Okay, so let's get going with our solutions review. Okay, so we've gone through this in class, but this will hopefully review some of it and remind you of some of the key things that we need when doing stoichiometry with solutions. Okay, so when we're talking about solutions in Chem, the main ones that we're talking about are anything where we have an aqueous solution, which means we have water as the solvent, okay? And the solvent is basically anything that is able to dissolve other substances. Water is the one that we will see mostly when we talk about different solutions in chemistry, but it is important for you to remember that other liquids can act as solvents as well. Okay, water is really good for us when we talk about it because it can dissolve ionic substances as well as being able to dissolve polar substances as well. So it has a very large range of substances of which it is able to dissolve. Okay, so a solution is any solution, so it's a mixture that is made up of one or more solutes, okay, which is our dissolved substances dissolved into a bulk solvent. Okay, so we could have a solution of NaCl and sugar, okay, because they would both dissolve in water, but when they dissolved, we wouldn't be able to see the individual particles, okay, so we'd be able to tell if it's a solution. Okay, so then the thing to remember here is that solutions are homogeneous, which means that they are the same all the way throughout. Okay, so they are the same throughout the bulk of the substance. We don't have parts that would be different to other parts. When we dissolve something in water, it is an aqueous solution and it will always be clear, but not necessarily colorless. Okay, so when we think about this, aqueous solutions could include cordial, it could include things like fruit juice without the pulp, and things like that. Okay, if it's fruit juice with the pulp, then we've got a mixture where we have a solid as well as dissolved substances as well, which is the fleshy pulp. Solutions are clear, which means we can see through them, but they're not necessarily colorless. If we think of something like Coke, so Coca-Cola, we can see that it's very dark, but when we shine light through it, we can still sort of see that the light goes through. So that's clear, but it definitely has a color, that dark brown color. Okay, if a solid dissolves in a solvent, it is said to be soluble. Okay, and if it doesn't dissolve, it is insoluble. And it's important to remember that we have a range of solubility. Some things are more soluble than others. It's not a flick a switch yes or no, it's a range of different things. So there is a certain amount of stuff that we can dissolve into a solution before we can't get any more in there. Okay, so let's look at concentration. So this, I think, is starting to confuse a few of you, but essentially concentration is how concentrated something is, how much of a substance is dissolved into a solution. Okay, so this is a quantitative measure of the amount of actual substance in a certain volume. Okay, so in IB, we are looking at this grams per decimeter cubed or mole per decimeter cubed, remembering that 1 decimeter cubed is equal to 1 liter. Okay, so in IB we use decimeters cubed, but it is important for you to not freak out too much by this, and just remember that when we say a decimeter cubed, we're talking about a liter, and you're really familiar with liters as volumes. Okay, so this is just a different unit, but it means the same thing. Okay, it would still be the same amount of solution. Okay, so when we're talking about grams per decimeter cubed, that would just be a measure in mass by grams divided by decimeters cubed. So I could have 5 grams of sugar in 1 liter. Okay, so that would be a 5 grams per liter concentration. Okay, so but the other one that we do is moles per decimeter cubed. To have moles per decimeter cubed, I would need to convert this mass into a number of mole first. But what we're talking about still, regardless of whether it's mole or grams, is the amount of substance present in 1 liter of solution, okay, or 1 decimeter of solution. We can see concentrations in many other units, including parts per million, milligrams per decimeter cubed, parts per billion, and things like that. The most important one, and especially the only one that you need to deal with at this point in time, is our moles per decimeter cubed, and remembering that if we have grams, we can convert to mole. So when we look at calculating our concentration, the formula you need to know is that concentration is equal to the number of mole divided by the volume, or the number of mole is equal to concentration times volume. Don't get them mixed up. As I've pointed out in class, this is a formula that for some reason I mix up in my head all the time, so I always write it down before I do any calculations. When we are using this formula, we need to be aware that by using this, because we are dividing mole by our volume, our units of concentration using this formula will always be moles per decimeter cubed. For N, it's little mole, and little n is mole and always will be. V is volume of solution, which is decimeters cubed in this case. So if our volume is given in centimeters cubed, we must convert. Okay, you need to convert, and we do that in the same way as when we convert milliliters to liters, which means we multiply by 10 to the negative 3, which is exactly the same as dividing by 1,000. Okay, so we need to make sure that we have all those units in as per the formula. Let's have a look at a couple of questions. You should have done these ones already, but let's just get them done here. So if we calculate the concentration, so this means that we're looking for C and we're told it's moles per decimeter cubed. If I have a look at this, the units are telling me what I actually need to do, because moles per decimeter cubed would be mole per decimeter cubed, means that I need to take my number of mole and divide by my decimeters cubed. This question says I have 5 mole of sodium chloride dissolved in 10 decimeters cubed, so C is going to be equal to 5 divided by 10, which is going to be 0.5. And its concentration, so it's moles per decimeter cubed. Okay, concentration in moles per decimeter cubed, looking for the same thing again, of 40 grams this time of sucrose, okay, dissolved in 250 centimeters cubed. In this case, there's a couple of steps that we need to follow in order to be able to work this out. I have a formula, so this means that I have a molar mass, okay, and if I add all this up, which is 12 lots of 12, 22 lots of 1, and 11 lots of 16. If I add this together, I will get 342 grams per mole is the molar mass of sucrose. 250 centimeters cubed, well, it's centimeters cubed, so I need to convert that to decimeters cubed. So this is going to be equal to 250 divided by 1,000 decimeters cubed, which is 0.25 decimeters cubed. Okay, so now I have volume where I want it, but I still have a mass and a molar mass. I want concentration, so I'm looking for number of mole over volume. I need this one. N is going to be equal to my mass of sucrose divided by my molar mass, which is going to be equal to, if I've worked this out correctly here, 0.117 mole. Now I have a number of mole that I can substitute into this formula, so my overall concentration is going to be equal to 0.117 divided by 0.25, which is going to give me 0.468. It's a concentration, so it's going to be moles dm to the neg 3. Okay, so that's my final answer there. If we're looking at significant figures, in this case, this is 3, so we can leave it as 0.468 and don't truncate it. Okay, questions 3 and 4. Calculate the amount in mole of sodium hydroxide that will be required to make a 10 centimeters cubed solution of 0.825 mole. Okay, so this time we have 10 centimeters cubed. So first things, I need to divide that by 1,000, because I want to get it into decimeters cubed. Okay, so that's going to be 0.01 decimeters cubed. Okay, I need the amount in moles, so I'm actually looking for N. Okay, I have a concentration and I have a volume. So if N is equal to C on V, okay, I want to find N. Oops, there I go. Told you I get this one wrong. N is equal to C times V, not C on V. Okay, so if N is equal to C times V, I'm going to get 0.825 multiplied by 0.01. Okay, and that is going to give me 0.00825, and that will be my number of mole. Okay, answer finished. Okay, so we could also write this as 8.25 times 10 to the negative 3 mole. Small amount. Amount in grams of sulfuric acid that will be required to make a 300 centimeter cube solution of 0.513 moles per decimeter cubed. Again, I need to divide by 1,000 here, which will give me 0.3 decimeters cubed. 0.513 moles per decimeter cubed. Well, this is a concentration. This is a volume. I need amount in grams. Okay, the only way I can get to grams is via mole. So because I have C and V, N is equal to C times V. So if we can work out a number of mole, we should. So we get 0.513 multiplied by 0.3 will give us 0.1539 mole. Okay, so that is the amount. Whoa, what happened there? Let's have a look. That is the amount of H2SO4 in mole, but I want to work out the amount in grams. So the only formula that we currently know to link grams and mole, N is equal to M on MR. If I rearrange for mass, I'm going to get mass is equal to N times MR. I have N over here, 0.1539, and then I just need MR of H2SO4, okay, which is going to be 2, because that's 2 times 1, plus 32.1, which is sulfur, plus 64, and if we put all of that into our calculator, we should get approximately 15.60 grams of H2SO4 is what we would need to measure out and then take up to a volume of 300 ml or 0.3 decimeters cubed. Okay, so that is standard working out calculation using mass or volume and number of mole. Okay, so molar concentration refers to the amount of solute that has been dissolved in a given volume of water, so the amount of stuff in a given volume. Okay, and then if we look at this, it's important to remember when we're talking about what that means is if we have 1 mole of decimeter cubed of HCl, we have 1 mole of HCl molecules per decimeter cubed of water, but because this has got 1 hydrogen, it would be 1 mole of hydrogen ions and 1 mole of chloride ions. Okay, so with respect to hydrogen ions, the concentration would be 1 mole per decimeter cubed. With respect to chloride ions, the concentration would be 1 mole per decimeter cubed. And with respect to hydrogen chloride molecules, it would be 1 mole per decimeter cubed. It changes if we look at the coefficients of that molecule changing. Okay, and that's what the next couple of questions are on. So what this one is saying is if I had 0.5 mole of decimeter cubed of copper 2 sulfate, so CuSO4, because copper 2 plus and SO4 2 minus, what would the concentration of the ions be? Now, it's 0.5 mole per decimeter cubed of this species, I have one of these. So with respect to Cu2+, it would be 0.5 moles per decimeter cubed. With respect to SO4 2-, it would be 0.5 moles per decimeter cubed as well, because I have one SO4 2- per copper sulfate, I have one Cu2+ per copper sulfate. If we look at the mole, what about 0.25 mole per decimeter cubed of nickel 2 chloride? This time we need to look at the fact that for every nickel 2 chloride, so nickel 2 chloride is 2 nickel ions, okay, it would be 1:1. So in this case, again, so with respect to nickel 2+, it would be 0.25 mole per decimeter cubed. When we look at the chloride, though, we've got a different ratio. So now, if I look at with respect to chloride ions, nickel chloride is to chloride ions. For every one nickel chloride, I'm going to have 2 chloride ions, which means that I will have a 2:1 ratio. So in that case, if I have 0.25 mole per decimeter cubed of nickel chloride, I'm going to have 2 times that, okay, can cross multiply here, of chloride ions. So my concentration with respect to Cl- is actually going to equal 2 times 0.25, which is going to be 0.5 moles per decimeter cubed. Okay, because I have 2 chlorides for every 1 nickel chloride that I have. And for 2 mole of ammonium sulfate, well, in this case, I have 2 lots of ammonium to every 1 lot of sulfate. So it would be 4 moles per decimeter cubed of ammonium ions. And it would be 2 mole per decimeter cubed of sulfate ions. Okay, so I'm going to leave this video here, and then I will do the next part of our calculations looking at dilution in another video.